All right, hope all of you are settled down in this course. I've scheduled your test one for next Thursday, not this Thursday, next Thursday. Okay, so if you go in Canvas and look under modules, you would see where to find it. Okay, so that's where we would take all our tests. There's nothing this week. We'll be finishing chapter one probably tomorrow, and then that is mostly what it's going to be on test number one. Okay. Before we start, can people hear me online? Okay. Yeah. Can you see the chalkboard? There's plenty of stuff written on it. Can you see it? All right. Any questions before we start? No? Okay. Let me just remind you of what we were doing yesterday, and then we'll jump into some applications today. Okay. So in section 1.3, we were doing separable differential equations, which are, we're looking at first order equations, which means only the first derivative is there, okay, which is of this form, f of x times g of y. And the whole idea is that, of course, this is dy dx. We could separate the x and the y functions to either side of the equation and then integrate both sides, right? So dy over g of y equal to f of x dx, integrate both sides. And assuming that you are able to do the integration, you'll get two functions on both sides. Okay, so this is going to give you some function of y. And this is going to give you some function of x plus c. Okay. Now that is a partial solution there, right? We have made some progress, and this is what we call as the implicit general solution. It's general because of that constant c. Okay. And then if you're able to do it further and simplify and find y equal to something, that is what we call as the explicit general solution. And we did a few examples yesterday with both these possibilities. And of course, there are two components to it. First is the calculus part where you have to do the integration. And then there is some algebra involved, which you need to know in terms of both separating this function from here to here and also to solve for y. Okay, those are usually some high school algebra that you have to know. The two other things we just did yesterday were completing the squares and partial fractions, which I think I mentioned that this is going to be a very important pair of techniques you will need later in the semester. Okay, so please review those things if you've forgotten it. Almost the whole of chapter 3 is based on those two techniques. Okay. So that's why those are important. We also started doing initial value problems where you're given, say, y of some initial value x equal to a equal to b. Okay, that will help you find the value of c. And in that case, the solution becomes more unique. It's called a particular solution. And this word initial can be a little misleading here. Okay, this I is for initial. It doesn't have to be always starting at t equal to 0 or x equal to 0. It could be some arbitrary point of time or space where you're starting your problem. Okay, that is your initial value there. And that will help you get a solution which is more unique, because with the constant c, there are infinitely many answers. This is unique. Okay, so that is where we stopped yesterday. All right, so we'll do one more example and then start an application. Any questions about any of those things I've written there? Anyone online, any questions? All right, one more example. Solve the initial value problem. Divide dx equal to 3x times e to the power of negative x minus y with y of 0 equal to 0. Y of 0 doesn't always have to be equal to 0 just for this problem. Okay. So can you try that and see how that it looks very similar to the problem we did before this. Okay, if you look at the last example we did yesterday, kind of looks very similar to this, but it's not the same. So can you get started and then I'll start doing it a few minutes later. So I hope this would be a natural thing to do. Okay, so just separate the e to the power of negative x and e to the power of negative y, and you can multiply both sides by e to the power of y so that the functions are separated, right? Okay, so the left hand side is pretty easy. How do you do this integral here? By parts, is that what if you agree? Integration by parts here. Okay. That's the only thing we didn't do yesterday in any of the examples. Okay, so we did substitution in a couple of examples. Parts is the other technique that I would like you to know in this chapter. Okay. And if you forgot what integration by parts looks like for any of these functions, integration by parts is the natural choice, okay, where k is of course not equal to 0. Okay. And n could be any positive number. If n is equal to 0, there is nothing useful there. Okay, so for all these cases, you could do integration by parts. And if you have seen calculus 2, or maybe some of you do it in calculus 1, okay, if you define your u and v carefully, it's just reversal of the product rule. The integral of u dv is uv minus integral of v du. It's very important that you pick your u and dv carefully, because otherwise this won't work. Okay. So in all these three cases, your u is always going to be x to the power of n, and dv is going to be whatever the other thing is. Okay. So all these three cases, the dv would be either e to the power of kx, or sine of kx, or cosine of kx. So that's just for those of you who forgot how to do integration by parts. But if you've never done it, you need to go and kind of look up any of the basic calculus 1 or 2 textbooks. All right. So in this case, we have a 3 here, which is not really playing any role for the integration by parts. Okay. So we have n equal to 1 and k equal to -1. So we can do integration by parts here with u equal to, if you want, you can take a 3 with it so that you don't forget it later. Okay, so u equal to 3x and dv equal to e to the power of -x dx. Yep. So from u, you have to find du, and from dv, you have to find v. Okay, that is what we need to put into that formula there for the integration by parts. Okay. That got really dirty there. It'll get worse. Since all of us are wearing masks, the chalk dust may not shift us. All right, so du is 3 dx, and v is going to be the integral of e to the power of -x dx. And I hope all of you remember this, that the integral of e to the power of kx dx is 1 over k e to the power of kx plus c. So this is negative e to the power of -x. That k is -1. We don't want to put plus c everywhere and confuse things, so we just need to put everything for the last step. So we have uv minus the integral of v du equal to 3x times negative e to the power of -x minus the integral of v, which is negative e to the power of -x times du, which is 3 dx. So this is uv minus the integral of v du. All right, there's nothing much to do here. Okay, this one has one more integral to do. Before that, let's just clean up that double negative and make it a positive. So that's going to be -3 x e to the power of -x. Okay. So it's going to be plus 3 times integral of e to the power of -x dx, which once again becomes negative e to the power of -x. So it's going to be -3 x e to the power of -x minus 3 e to the power of -x. Now you can put your plus c. Again, please slow me down if I'm going too fast, okay, or if there's something that is not making sense. All right, don't forget we started our story here, okay. So the left-hand side is still that term. So it's e to the power of y equal to all this bunch of terms here. So back to what we were doing. From there, e to the power of y equal to negative 3x e to the power of negative x minus 3 e to the power of negative x plus c. Go to take a pair of scissors and cut that off. I don't know what to do with this. If I put it like this, is this kind of blocking your view, or is it okay if I leave it like this? All right, y of 0 equal to 0. Let's do that. Okay. That's going to be 1 equal to negative 3 plus c. So c is 4. So back to our solution there. That's going to be e to the power of y that's going to be e to the power of y equal to negative 3 x e to the power of negative x minus 3 e to the power of negative x plus 4. And now take logarithm on both sides. So y equal to the ln of absolute value of 4 minus 3x e to the power of negative x minus 3 e to the power of negative x. Now you need to know where to stop these problems. Okay, this is probably the best and only place where it could stop. Okay, if you go any further, you're going to make all kinds of unnecessary mistakes. Okay, this is not equal to ln of 4 minus some students, they're surprised when they know that this is not true, because natural log function is not a linear function. Okay, so you cannot just distribute it over. So you should stop here. Okay, if you write this is the wrong answer. Okay, because in general, the logarithm of a plus b is not usually the question would specify whether it's an explicit or implicit. So if nothing is mentioned in the question, it's implied, it's explicit, that is expected. Okay, so always play it safe by writing the explicit solution. Okay. If it is something that you cannot solve, then usually I put it in the question, do it implicitly, and that should be clear. Okay. All right, any questions about this one? So be prepared to do some integration by parts on your test 1 next week. Yep. Do we need the absolute value? Let's see. Yeah, maybe not. In this case, I think this quantity is always positive here. So yeah, it's safe, probably safe to not put the absolute value there. Any other questions? Yep. When? Yeah. Because if we were not sure about what exactly is happening inside that quantity there, so if you write like this, okay, and what if x equal to, say, negative x equal to 2, for example, okay, then the logarithm of this quantity is not defined. So to avoid that kind of a situation, you put the absolute value so that the function is defined in the domain. Okay, that is when it's required. In this case, e to the power of negative x is going to be a pretty sharply decreasing function, so this 4 is going to dominate both these terms. That is why in some cases it's safe to not put it, but it doesn't hurt if you just put it all the time. Does that answer your question? So did that answer your question?
Yeah.
All right. Any other questions about this? All right, now let's do an application. Okay. And some of you may have seen this application in physics or thermodynamics. Okay. And it's the same concept. It's called Newton's law of cooling. So this is a real physics application or a science application. It's not one of those fake applications where you're building a fence around a garden or something. Okay. All right, what is the setup of the problem? Well, you can think about a hot cup of coffee. Okay. I'm going to use degrees Celsius because it's more natural to me. So 100 degrees Celsius is boiling water. Okay, it's really hot. And it's sitting in this room, which is at 20 degrees Celsius, which is pretty comfortable setting. Okay, you don't need any heater or air conditioning or anything. Okay. And you also have a can of cold soda. Okay. Keep it closed. And let's assume that it's really just took it out of the freezer. Okay, so it's at 0 degrees Celsius, same room. So it's kept in this room here. Okay. And if you were to plot the graph of temperature with time for both these things there, okay, and assuming that this is 0, and this is 100, and this is 20 here, okay. What kind of behavior do you expect if you just let them sit there, if you don't do anything else to it? Okay, you don't put them in a microwave or something and just let them have their own natural behavior. What do you expect in course of time? Yeah. Yes, so her answer is that it's going to approach at 20 degrees. Is it going to approach like this? Or is it going to be a slow approach to 20 degrees? Slow approach, right? I mean, we have all observed that you put some hot coffee here, cools down slowly, right? So this is what you would observe. At some point, we expect it to be getting as close as possible to 20. And similarly here, this will start warming up, but it's not going to start boiling, right? All of us know that. Just going to increase and eventually just almost hit that. Okay. This is what you call as thermodynamic equilibrium, right? Well, Isaac Newton was pretty smart. Okay, he figured out that there is a nice way to model this simple process. Okay. So if you denote your temperature by capital T, doesn't matter what units you use. And if you denote little t to be the time, you just need to be careful about when you say T, you have to be careful about whether it's capital T or small t. Okay. Then the rate of change of temperature with respect to time is proportional to, I think all of you are familiar with that alpha-like thing, tells you it's proportional to the difference in temperature between what you have, maybe it's a coffee or the cold soda, okay, and the surroundings. We use A for ambient, okay, so this is the ambient temperature. What's called the room temperature. So that is a fixed value. You could say that, oh, it keeps changing, but you know, it's an idealized situation here. We don't want to make it too complicated. Okay, so we are going to fix the room temperature, and T is the temperature of the object, whether it's the coffee or the soda or a block of ice, okay, of the object. It's a very simple law, right? There is nothing fancy about it. So the rate of change of temperature is proportional to the difference in temperature. So you can imagine what's going on here. The difference keeps on decreasing with time. Eventually, it's equilibrium. So if you remove this proportionality constant or proportionality symbol, you get a constant there. So you have dt dt equal to some constant k times t minus a. I know some textbooks put a negative there, it doesn't matter. Okay. Just follow one thing and you should be okay. So if you put a negative there, just put negative all the time, or don't put negative, don't put negative. Okay. So don't confuse the two notations. The mathematics will take care of it, irrespective of how you do this. Okay. What is k? K is a constant. Now, when you say it's a constant, it has some physical meaning and units and so on. Okay, so you can't be just saying it's some arbitrary constant. So k is a constant that depends on the properties of the material. Okay. Of the object that is being cooled down or warmed up. Okay, so depends on what kind of cup is holding the coffee or what kind of liquid you have in there. So there are a lot of things that affects that constant k, right? And it has got some units. So this is the rate of change of temperature with time. This is temperature, okay? And the units have to match on both sides. So we have to be careful about what this k actually represents here. So we have dt dt k times t minus a. This is degrees Celsius over time. Okay, so degrees Celsius per second, for example. And this is degrees Celsius. So the units of k has to be per second. Okay. If you take a real thermodynamics course, you would see a bunch of things in there like density and specific heat and so on, which will eventually kind of clump into that constant k. Okay, so we are not really going to dissect it and look at all the dirty details in there, but that is a constant that is going to be kind of covering all the other physical properties of this problem. Okay. But for our purposes, it's a nice separable equation. Okay, that is all we care about. So dt dt is k times t minus a. Ask a question whether, what happens if k depends on time. Then it becomes a more complicated problem. It becomes a nonlinear equation and so on. But for the time being, it's just a constant. So it doesn't change with time or with temperature. Okay. So we can separate this. So you have dt over t minus a equal to k dt. Integrate both sides. Nothing fancy here. This is going to be the logarithm of the absolute value of t minus a. So once again, that shows you what the absolute value is doing there. If t is greater than a or less than a, it would adjust the sign. Okay. Equal to kt plus some constant c1. Kind of reserving the c for later use. So kt plus c1, raise both sides to the power of e. So it's going to be t minus a equal to e to the power of kt plus c1. And we did this yesterday. If you have e to the power of something like this, you can call the e to the power of c1 as a constant c. So that's going to be c times e to the power of kt. Because you have lots of exponents which will separate these two. So t, which is what we are trying to find here as a function of time, equal to a, which is the ambient temperature. We should know this, okay, plus this term that depends on the time t, that's going to be a plus c e to the power of kt. I don't want you to use this formula kind of as a cooked up thing in every problem, okay, that doesn't serve any purpose. So when you're doing this problem, always start from the differential equation. That is why you're doing this course. Okay. It's a very simple equation, right? Just start with this, show your work, separating the equation, solve it, and then write it. Please don't just write the formula and start plugging in numbers. That is for high school students. So please do not use this directly. Especially when you're doing it on a test or a test next week, right? You don't want to just say, oh, I know the value of this, I know the value of this, let's just plug it in, and here is the answer. Anybody can do that. Okay, so I want you to show me what kind of differential equation you're using, how you're solving it, and then okay, it's not a big deal. All right, any questions about that derivation? Yep. It's a linear function according to this, yes. Yep. When it's a linear function, well, this is not a linear function, right? The rate of change is a linear function. And this would kind of agree with the shape of the graph given there is an exponential growth or decay depending on the value of k, right? If the k is positive, it's exponential growth. K is negative, it's exponential decay. Okay. Any other questions about this? So these are word problems. So you have to read the question, understand what is given in the question, okay, give some values and some variables and set up the problem, then do it. So let's do a couple of those. See how it works. And you need a scientific calculator to do this because not all the numbers are going to be easy to just do by quick calculations. Okay, so have a calculator handy. Even the one on your cell phone should do. All right, let's write down this problem then. Again, those who are online, please type any questions if you have, okay, so that if others can also benefit from it. So example 1. An object's temperature at t equal to 0 is 5 degrees Celsius. Okay, that is pretty cold. In case you are not familiar with the degree Celsius scale, okay, 0 is melting, 5 is pretty cold. And after 5 minutes, it is 8 degrees Celsius. Even if the law is called Newton's law of cooling, it applies to both warming and cooling. Okay, that's just the way the theorem is named. Doesn't mean that you cannot do it for the other one. The room temperature is 20. Degrees Celsius. Find the temperature as a function of time and also the temperature after 30 minutes. As a function of time. So that is the general expression for the temperature and its value. After 30 minutes. So one thing you will observe here is that all the time units here are in minutes. Okay, there is no need to convert it into anything else. Okay, so you don't have to sit down and convert this into hours and make it more complicated. So just use everything in minutes. Okay. And all the temperature units are in degrees Celsius, so that's good. All right. I have no idea what I just did up there. Okay, so I'm going to start from scratch. So if T is the temperature by Newton's law of cooling, So just showing you what you're supposed to do when you get a problem like this. Okay, don't just go and start with what I boxed there. So by Newton's law, we know that the rate of change of temperature with time is some constant times T minus A. You cannot derive this, right? This was something that is a postulate that Newton proposed based on observation. Okay, you cannot derive that formula, but you can derive this one by solving the differential equation. So dt over T minus A equal to K dt. K is a constant. So that's a separation there, ln of T minus A. And with some practice, you know what is coming, right? So you have KT plus C or C1, I don't care what you call it. And then it doesn't hurt if you just write T equal to A plus C e to the power of KT. Okay, so at least that means if you write, I know that you have understood what is going on here. You're able to write this problem in terms of a differential equation, solve it, and write the solution. Okay. So when I first tell it to students, like, oh, I don't want to write all that stuff, but it's not too much. Okay. All right. Now the question is, what is what? Okay. We need to give some letters to all those things in the problem. Okay. You know the room temperature is 20. Let's take care of that first. A is 20. That's not going to change. Okay. What else is given there? You're given the temperature at 0 equal to 5. And the temperature at some other time. You might be wondering why we need two different values, and we'll see that soon. Okay. Temperature at 5 is equal to 8. Okay, that's all we know. Well, it's at least warming up. Okay. Now, go to the solution here and try to kind of make some good decisions about what you can do. Okay. Let's make yourself the value at 0, because that's going to at least get rid of one of the constants and focus on the other one. So when t equal to 0, 5. So that's going to be 5 equal to A is 20. Okay, don't forget. Plus C times e to the power of 0, which is 1. Okay, so that is why doing the value at time t equal to 0 first, it's easier because you can get rid of one of the constants right away. So C is negative 15. So that's the easy one. Now let's do the second one, T of 5 equal to 8. So 8 equal to, the room temperature hasn't changed, it's still 20. You know C is negative 15 times e to the power of k, which we don't know, okay. And little t is 5, so it's going to be 5k. So that is why we need two values, because we have two constants there, a and c. Okay. A is always obtained from the initial value, and k is obtained from the other value. All right, I hope all of you know how to solve these kinds of pre-calculus equations. Okay, so subtract 20 on both sides, you have negative 12 equal to negative 15 times e to the power of 5k. And divide both sides by negative 15, you get 12 over 15, which is 4/5. 0.8 equal to e to the power of 5k. So up to there, I can do without a calculator. Okay. So after this, I have no idea. So 5K equal to the natural log of 0.8 and K equal to logarithm of 0.8 over 5. And that's where I need your help. Just need 2 or 3 decimal values. Negative 0. Okay, that's good enough. Yeah, you don't need to give 15 more values after this. Okay, it's not going to do any favor. So, all right. So we have everything now. We have C, we have K, we have A. We have a complete expression now for the temperature at T. So T of T, based on all these calculations down here, would be 20 minus 15 e to the power of negative 0.045 T. Put them in the right place. So that is what it means by saying find temperature as a function of time. Okay, this is the answer for that part. Any questions on that calculation there? All of you are comfortable with this? Now, can you tell me what the temperature after 30 minutes would be? Just plug in 30 here and what do you expect? Is it going to be less than 20 or more than 20? You know, we should have some kind of a physical feeling of this problem. Yeah, less than 20. Okay, so what do you get if you do the calculation? Okay, looks like that is less than 20. So at least the answer makes sense. Now, if you get the answer to this question as say 5,000 degrees Celsius, something is wrong. Okay, so just check your calculations. Don't just say that, oh, that's how math works. We get weird things. Yeah. The limiting case is when T goes to positive infinity. Okay, that's never going to achieve mathematically, right? So in the physical world, yes, it does achieve 20, but mathematically it was when T goes to infinity. So again, if you get some kind of meaningless answers to these kinds of problems, always check, okay, because Mr. Isaac Newton is always correct. Okay, so you have to trust his model. Any questions on this? Let's do another one. Okay, this is going to be a little bit depressing to some of you, but number 2, going to erase all of these. All right, here comes the story. Example 2, a dead body is found. Sorry about this. So we're going to play a detective's role here. At 1:30 p.m. at 32.5 degrees Celsius. That's a pretty warm room. Okay, 32.5 degrees Fahrenheit would be freezing, but degrees Celsius is kind of uncomfortable. At 2:30 p.m. the temperature of the body is Let me ask you this, what do you think it's going to be? Is it going to be less than 32.5 or more than 32.5? It's a dead body. Less than, okay, body cools down, unfortunately. 30.3. The room temperature is still 20 degrees Celsius. So the dead body is found at 1:30 p.m. at this temperature. An hour later, it's cooled down. The room temperature is fixed. When did this person die? Or at what time did the death occur? Okay. Now, I don't know if the problem is complete. It may be lacking some information here. So that's that's for you to figure out if you need more values to complete this problem or if you have all the information. So can you start doing it and then let's see. So part of the question is to kind of make sure that you make good use of the data given to you. So I'm just writing the differential equations part, okay, which should be pretty routine for all these problems. So nothing new in terms of solving this. At this point, if any of you feel like there is some kind of missing information, let me know. Yeah.
There's no initial value for the time.
In
You
it-
can't find the constant.
There is no initial value for the time.
You can't plug in t equals 0. So it always end up with that. And t equals.
All right. So I kind of get what you're saying. Is there an easier way to just put that What is missing here? What the normal body temperature is. Okay, so the normal body temperature is so in degrees Celsius. What is that value? It is not 98. Okay, 37. 98 degrees Celsius is almost boiling water. That's not something you want on your body. So it's 37. All right, so I think some of you online also had the same question. So we need that information for the problem. Otherwise, you cannot kind of trace back in time. All right, it's better to do this problem if you start at 1:30 p.m. as your time t equal to 0. Okay, kind of makes your problem a lot easier to calculate. So 1:30 p.m., let's keep that as t equal to 0. So later when you get your answer, you have to kind of go back from t equal to 0 backwards. That's okay. Otherwise, there'll be too many other constants to solve for. So based on this, t of 0 is going to be 32.5. So how do you write the value at 2:30 p.m.? What is the mathematical way of representing that here? Yeah, t of 1, because we just need to do it in terms of hours. Okay, you don't have to convert this into minutes or seconds or anything and complicate things. So t of 1 is equal to 30.3. So if you plug it in there, the t of 0 should give you 32.5 equal to 20 plus c times c to the power of 0, which is 1. Okay, so c is 12.5. And if you plug in t equal to 1, you get 30.3 equal to 20 plus 12.5 e to the power of k, t is 1. Okay. Do your regular pre-calculus there. Okay, so it's going to be e to the power of k equal to 10.3 over 12.5, or k equal to the natural log of 10.3 over 12.5, which is negative 0.194. Okay. When you're doing these problems on the test, please do the calculations. Okay, don't just leave it like this and ask me to do the things myself. Okay, so just have a calculator handy and do it. All right, so we have all the constants we need. So from there, we have t of t equal to 20 plus 12.5 e to the power of negative 0.194 t. Okay, t is time. So that is the general change of temperature with respect to time for this problem, okay, based on the given data. Now we need to find when the body temperature was 37. Okay, at some point in the past, it used to be 37, and we need to find what this t would be. Okay, so have to find t such that t equal to 37. Now that answer is going to be coming out as negative because we started at t equal to 0. Okay, so anything in the past that should be coming out as negative. So this is 37 equal to 20 plus 12.5 e to the power of negative 0.194 t. Every time there is only one unknown quantity to be found, little t is the one here. All right, do the math. So you have e to the power of negative 0.194t equal to 17 over 12.5. Or t equal to ln of 17 over 12.5 divided by negative 0.194. What is that equal to? Any wild guesses about this? Negative 1.58 hours. It's not 1 minute or 1 hour 58 seconds. Okay, that is 1.5. It's almost negative 1.6 hours. Just a few minutes this way or that way is not going to change the story a lot. Remember, we started at 1:30 p.m. Okay, this was at t equal to 0, and we are going backwards now. Okay, if it was 1.5 hours, it would have been 11 a.m. right? T equal to negative, right? No, 12 p.m. Negative 1.5 hours would have been 12 noon. Is that right? So 0.1 hour would kind of shift it backwards by around 6 minutes. Okay. So negative 1.6 hours would be approximately 11:54 a.m. But this is okay as well, because the time of death is never a precise value anyway. Okay, so even if you're off by 5 or 6 minutes, nothing is going to change. But if you really want an accurate answer based on what you have done, it's going to be close to 11:54 a.m. Okay. All right, so that is what your typical Newton's law of cooling or warming problems look like. Okay. Any questions on this thing? This officially finishes section 1.3. So all those separable equations we did yesterday and today, and also the Newton's law of cooling. Okay, so you can go ahead and finish off all the homework questions in 1.4, so 1.3 today, and compare your answers with the solutions posted. I hope all of you are aware that if you look in Canvas modules, you see the solutions to the homework. Some students, they find it out on the last day of the semester. All right, and my office hours start today. Okay, the link is posted announcements in Canvas. So if you have questions about the course or anything else, please feel free to stop by. If we don't have any questions, let's march on to section 1.4. All right, so again, we are looking at these differential equations in special classes because you can never solve a general differential equation randomly. Okay, so it's nice to kind of compartmentalize this and study them one by one. So we did separable equations, which were a first order. Okay. So here the first order means you only have dy dx. There's no second derivative term, and linear means not non-linear. No non-linear y terms. I hope all of you know what a non-linear term means. Okay, so y square is non-linear, e to the y is non-linear, sine of y is non-linear, square root of y is non-linear. Okay, none of these things should be here if it is a linear equation. Okay. So in general, a linear first order differential equation looks like this. a1 of x times dy dx plus a2 of x times y equal to some function, you can call it as g of x. Remember that there is no restriction on the x terms. Okay, they could be nonlinear. That's okay. So a1 of x is not equal to 0, because if that is equal to 0, there is nothing to solve. Okay. But otherwise, those are pretty unrestricted terms. A1 of x, a2 of x, and g of x can be anything. Well, when you say anything, we hope those are things we could differentiate or integrate easily, but they could be anything. Okay. So that is the most general form for a linear first order differential equation. What we'll do is we will divide by this leading coefficient throughout, okay, because it's not equal to 0, so there's no harm in doing it. So divide a1 of x and you get the differential equation with some rather weird looking constants. So we have dy dx plus a2 of x over a1 of x times y equal to g of x over a1 of x. You can call this ratio as some function p of x, and this has some other function, say q of x. That gives you a little bit more compact form for this linear first order equation. You have y prime plus p of x times y equal to q of x. This is what we call as the standard form for a linear first order equation. Okay, the coefficient of y prime is 1. We don't really care what p or q is. Okay, they could be anything. They could even be 0. In that case, there's nothing interesting going on. This is the standard form for a linear first order differential equation. So every time you get a problem in section 1.4, the first thing you have to make sure is that it's in the standard form. Okay. Only then whatever we are going to do is going to be applicable. Otherwise, things will be off by some weird functions and you may not be able to fix it. All right, so the question is then, how do you solve it? So how do we solve? Y prime plus p of x times y equal to q of x. In general, this equation is not separable. Okay, in some freak cases it might be, but usually this is not separable. I'm saying in general because there are some equations which are separable and you could do whatever we're going to do next. Okay, that's always there, but most of the equations we're going to see in the section are not separable. So then what is the other option? I hope all of you remember this. If you have a product of two functions here, and if you take the derivative, or if we know the product rule, So what you're going to do now is to kind of work this backwards from here to here. Okay, if you have a set of terms which are written like this, we could write it as a single derivative. So the idea here is to combine these two terms into a single term. It's a pretty ambitious thing to think about, okay, because right now there's a derivative here, no derivative here. Okay, it's a little bit messy at this point. Combine the left-hand side into a single derivative. Because if you are able to do it, then you can integrate both sides easily and then solve for y. Now I'm going to do a small derivation here. I don't ask derivations on tests or anything. So if you're not interested in derivations, just hold on. Okay, you can kind of relax for the next 5 or 6 minutes and then get back when we use the result. Okay, so it's up to you, whatever you're interested in. Okay. So I'm going to quickly derive what we're going to do. So we need to combine this into a single derivative. Okay, so let I of x be a magic term which will help us do this. So this as in this. Because it cannot just happen out of nothing. We have to do some manipulations. Okay, and let that magic term be I of x. We'll give it a more official name later. So I'm going to multiply I of x throughout. In the standard form. Okay, so it's going to be I of x times y prime plus I of x times p of x times y equal to I of x times q of x. There's absolutely nothing wrong. If you take an equation and multiply throughout by the same thing, nobody is going to get hurt. Okay, as long as you do it for each term here and it's not equal to 0. All right, so this is what you have here. Let's name this as star just for future reference. Let's also see what happens if you do the product rule on the product I of x times y of x. This is your calculus 1. So that's going to be I of x times y prime or dy dx. Now that seems to be the first term here. Okay, so far we are making some good progress here. Plus the next term is where things are going to get a little bit messy. Okay. Plus y times the derivative of I, which is di dx times y. Okay. That is the derivative of the product. Now, if these things have to match, okay, then this term here should equal this term. Because that's what you're trying to achieve here, right? We're going to write that term as a single derivative. So if you're able to do it, then the first term's already matched. Okay, this is already done. Then the second term should also match term by term. So this means that you have di dx times y equal to I of x times p of x times y. Only then these two are the same thing.
Professor, the
Can
people
cancel the y
online
on both
can't see the
sides.
board anymore.
And what you get is a separable equation. Okay. So you can write di over I equal to P of x dx.
Professor,
Are you able to see the
Professor,
camera?
we can't
or-
see the screen. No, we can't.
All right, is it back now? Phew, that was scary.
Yeah, it's back.
The last thing I want to do is teach for half an hour without the video. All right, so this is a separable equation. Integrate both sides. Okay, we are trying to find this magic term I. Okay, so the left-hand side is going to be the natural log of I. We don't know what the right-hand side is. It's just going to be the integral of P of x dx. That depends on what P of x is. And raise both sides to the power of e, and you get I of x equal to e to the power of integral of P of x dx. So this is the magic term that is going to help us achieve this goal. Okay. It looks a little uncomfortable because you have an exponential function with an integral at the top. Okay, so it's not the integral of e to the power of P of x. It's e to the power of integral of P of x. Okay. But apparently, if you do this right and you apply it there, we could collapse those two terms into a single derivative. The whole point of doing this is to get this term here. Okay. So this I of x equal to e to the power of integral of P of x dx is called the integrating factor . So this technique is called the method of integrating factor. Okay, so it helps us combine the two terms on the left-hand side into a single derivative each time you do this, okay, assuming that your calculation is correct. Okay, so you have to trust your calculations here. If you do this correct, you can always write left-hand side equal to this product, and then you can integrate from there. Okay. So let me just write down the summary of what you're doing. So those of you who kind of took a break during the derivation, come back. Okay. So it's kind of an algorithmic kind of a problem. Okay, just follow the step by step. You'll reach the answer, but do it carefully. Okay. So the procedure to find or to solve y prime plus p of x times y equal to q of x. Now, before you start doing this problem, make sure that the equation is in the standard form. Okay, if it is not, please convert in the standard form. So make sure that your differential equation is in the standard form. Okay, which means it should be in this form. Otherwise, you're just going to waste time doing some useless things. Okay. Find the integrating factor. You can call it as I of x equal to e to the power of integral of P of x dx. Get used to that function because it's not integral of e to the P of x, okay, which is more natural. This is e to the power of integral of P of x. One other advice I have for this particular step here is do not put any plus c here. We'll put all the plus c's later. Okay, we don't want to keep adding c's here and there and create this more confusing. So keep the integrating factor clear of any constants. Multiply I of x on both sides of this differential equation here. Okay, let's call the star. Some students, they skip the step. They say, oh, I know what to do. Okay. The problem is later they forget that you are supposed to do it on both sides, and then they end up with the wrong answer. So to be safe, just do the step. Okay. It's going to take what, 5 seconds. Combine the two terms on the left-hand side. As the integrating factor times y prime. This step is the key step. The reason why we're doing this painful procedure is so that we could write the left-hand side into a single derivative. Okay. So you found I of x from step 2, and we are able to write this as a single derivative. How do we know it's correct? That's why I derived it. Okay. So if you really doubt it, go back and check the derivation. Equal to I of x times Q of x. Because you multiplied I of x on both sides of the equation, so this is here. Okay. The only difference is that the left-hand side became one derivative. You have to believe in this. Okay. Otherwise, this technique is not going to work. Now you are in good shape. Integrate both sides with respect to x. Okay. I think that should be pretty obvious as to the fact that x is independent variable here. So integrate both sides with respect to x. Now here is the important thing. Put a plus c immediately. Okay, don't wait till the last step, and then solve for y. In this order. Okay. Not solve for y and then put c. Put c and solve for y. I'll tell you why. Okay. And that should be your final answer. You will get completely different answers in most of the questions if you flip these two things. Okay. So as soon as you do the integration, put c and then solve for y. All right, so that is going to be our main thing for section 1.4. Okay, so we'll do a bunch of problems today, and tomorrow we'll see the application. That's going to be our main theme. Okay. Before I erase this derivation here, do you have any questions? So each time any of you is going to ask me, how do you know that step 4 is true? I'm going to ask you to just go back and check this. Okay. Unfortunately, I won't be able to do it each time, so please keep this handy. All right, let's do a few examples then. This is a tricky section, okay, be careful. I forgot to check with the online crowd. Do you have any questions? But the chat thing disappeared. Gallery view. Okay, there you go. Okay, no questions. All right, examples. Example 1. X square y prime minus 3 xy equal to x to the power of 5. Okay, so it's a first order linear equation in y, okay, and the right hand side is x to the power of 5. Want to make sure that it's a clean problem. All right, so this is the question. So first example we are doing, so I'm just going to go through this step by step. Okay. So first thing is to make sure that it's in a standard form. So it is not. Okay, there is an x square multiplying here. So step 1 is to divide x square throughout. And that will make it y prime minus 3 over x times y equal to x to the power of 3. Now, some students, they don't simplify this all the way. They write it as x to the power of 5 divided by x squared, and then they do all kinds of things with when they integrate it. So, just simplify it. This is just middle school math. Okay, don't wait till things get worse to do that. Now, here are some very subtle things about this problem. Okay, the next step is to find the integrating factor. For this, we need to identify what p of x is. Okay. P of x in this case is whatever is multiplying y, which is going to be that term. That includes the negative sign. So if you don't include the negative sign, in some questions, it will give you all kinds of nasty things. Okay. So this is going to be e to the power of the integral of negative 3 over x dx. You can factor this negative 3 outside or pull it outside. It's going to be e to the power of negative 3 integral of 1 over x dx. And that's going to be e to the power of negative 3. And if you're not sure about what the value of x could be, you can put an absolute value there. We need to simplify this thing. Okay. This is not a very nice looking term. Can something from your high school tell you what this would reduce to in a nice way? Yeah.
Minus 3x, I think.
That is the tempting thing, minus 3x. It looks like minus 3x. It's not really minus 3x. Yeah.
Is it x to the negative 3?
It's x to the negative 3 because this negative 3 goes up there. Logarithms have a habit of pulling things to its exponent. Okay. So we have e to the power of ln of the power of negative 3. Then you can cancel the e and the ln. Okay, so please be careful about this step. Okay. And this is now equal to x to the negative 3. Now that the logarithm is gone, no need to worry about absolute value. So what is the property I'm using here? E to the power of a ln of x equal to x to the power of a. Just write it somewhere. Comes pretty handy for all these kinds of problems where we do integrating factor. So it's x to the power of negative 3, and that negative is going to make a difference. Okay. All right, let's keep going. So that is step number 2. I think I wrote different ways of writing 1s and 2. So that's step number 2. Step 3 is to multiply the integrating factor on both sides of the equation. So step 3, not example 3. Multiply x to the power of negative 3 on both sides of the equation, the standard form. Okay, so it's going to be y prime minus 3 over x times y equal to x to the power of negative 3 times x to the power of 3. So if you don't do this step, you might forget to remember that this side is actually equal to 1 and not x to the power of negative 3. And my claim is that if you have done everything right, this now is going to become x to the power of negative 3 times y prime. And this is just equal to 1. And you might be thinking, how do I know that? Okay. That's what I just derived earlier. Okay. If you're really doubting this, you can always do a product rule on this. Okay. You don't have to. If you just want to do your calculus 1 exercise of product rule, this is going to be x to the power of negative 3 times y prime plus y times the derivative of this, which is y times negative 3 x to the power of negative 4. Okay. And that is what you have here. X to the power of negative 3 times y prime. And then you have a minus 3. And you have x to the negative 3 over x, which is x to the negative 4. Okay, so it works. Okay, you are guaranteed that it is true. You don't have to check this each time. Okay. Now integrate both sides. So it's the integral of x to the power of -3 times y prime dx equal to the integral of 1 dx. The reason for doing all these integrating factor drama is so that the integral and the derivative cancels out, okay, by the fundamental theorem of calculus, and you just have this term. So we have x to the power of -3 times y equal to integral of 1 is x plus c. I'm following my own whatever I wrote earlier, that you integrate, put c immediately, don't wait 2 minutes later and then put it. Okay. And then multiply both sides by x to the power of 3. So you get y equal to x to the 4 plus c x to the power of 3. Okay. Now, if you are a keen observer, you can see why putting the c there is important, because c times x to the power of 3 is not a constant. Okay, it's a function. Right? Because with each value of x, it's going to keep changing. Okay, that is why if you did the integration and then solve for y and then put plus c here, you get a completely different answer, which is wrong. Okay, so the answer is not x to the power of 4 plus c, it's x to the power of 4 plus c x to the power of 3. So this is why don't forget it here. All right. Any questions on this? I'll let you do a quick example and then we'll stop. Okay. Example 2. Y prime plus 2xy equal to x. Just lesser drama compared to the previous one because it's already in the standard form, and you don't have to fight with E and Ln properties. Okay, so can you just try that quickly? I hope it works. I hope that is what he got as the integrating factor. There is nothing else they could do there. Yeah. So you don't have to do step 1, step 2, step 3 each time. Okay, once you get used to it, just follow the process. So if you multiply the integrating factor on both sides, you get this. Okay. Now, can somebody tell me what this is going to look like in the next step, following what we just learned? Yes, this is the takeaway from today's lecture, right? You should be able to do that. And you can always kind of visually check backwards. Product rule, this times y prime, y times this prime. Okay, it's there. Equal to xc to the power of x square. Now integrate both sides, and you get e to the power of x square times y equal to the integral of x e to the power of x square dx plus c. And I told you yesterday that integration by substitution will pop up here and there. Okay, here it is. U equal to x square. So du would be 2x dx. Or 1/2 du is x dx. So e to the power of x square times y. One half times the integral of e to the power of u du, which is e to the power of x square plus c. Okay, kind of did that a little fast. So if you need more steps, let me know. Okay. And divide both sides by e to the power of x square. You get y equal to 1/2 plus c e to the power of negative x square. Okay. It's one of those problems where if you forget to put plus c, you'll get funny answers like y equal to half. Okay. So please be careful about remembering to put your c for integration. Otherwise, it's a pretty standard process. We'll do a few more examples tomorrow and we'll do applications. Okay. All right, that's it for today. Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Going to stop recording this.